Yeah, the formula you show on this page, the EVE formula is derived for massless fermions at equilibrium. And when we talk about lambda or other hyperon polarizations, they are very massive. So when you apply this EVE formula to describe the polarization of like hyperon, should you also consider the mass correction? As far as I know, there is a mass correction to the EVE formula if you consider massive fermions.
Okay.
Yeah, and also because this formula is derived for massless fermion, and for massless fermion, the spin is always locked with the momentum. So if momentum is thermalized, which means spin should also be thermalized.
Right.
So on this part, yeah, for this part, I agree with Francesco that this formula is true for thermal equilibrium, also for spin, for spin thermal equilibrium.
Let me say that's not the answer to your question. These are some feelings, I would say.
Okay.
That of course you're right, because even if we are at the level of quarks, strange quarks are not that light as U and D quarks. Okay. If we go further to the level of hadrons, of course, K meson isn't a pi meson with mass. So that old activity about partial axial current conservation, if somebody remember this, it was formulated in terms of pion and nucleon degrees of freedom. So, okay, nucleon are not massless at all, like lambda, but pion is okay, it is light. So if we here consider similar story for the strange sector. Of course, in the strange sector, it is not that good as for pion and nucleons. But still, I hope that there could be, it could be formulated strange partial conservation of strange axial current. So somehow it is not conserved to the degree of non-zero Kian mass, but still there are some, should be some remnants of this conservation. Of course, this formula for the exact chiral symmetry, so it is inapplicable. Strictly speaking, it is unapplicable. So it should be corrected. How it is corrected, it is the matter of further work. So maybe the truth is in between these coalescence lies like hadronization and the conservation of axial current. Okay. Therefore, I don't exclude this possibility, and maybe the truth is somewhere in between.
Okay, thank you for your answering. Okay, so we have now 2 more questions. I would like also to encourage people just to maybe ask questions about the 2 previous talks, not only to continue with Yuri's talk, but of course, we can do as you wish. Yeah, so Giorgio, please.
I mean, I think thank you, Francesco and others for asking this is a thing that I've been worried for a long time, that the question is, to what extent are the different things presented here different physical processes, and to what extent are they models? I mean, by the last definition, the only difference between the thermodynamics and Yuri's and the chiral vortical / axial effect is that in one case you have chemical like detailed balance between spin and momentum, and in the other case you don't. Is that the issue? That's certainly a physical effect, and no one really knows. And no one really knows to what extent is spin chemically equilibrated with vorticity. And this is important, and it would be the statement, if spin is equilibrated with vorticity versus if spin is versus not, there is a different polarization dependence on energy. That's an important thing to know, but I would say that the terminology is really confusing because the axial vortical effect is also a thermodynamic thing. It's a function of temperature and chemical potential.
Let me answer. Sorry, I am again lost. Do you hear me?
Yes, yes, we hear you.
Okay, that because I have lost my Zoom and I don't know where it is on my computer.
Zoom didn't
but okay, if you hear me, that's okay. The true thermodynamical approach doesn't need anything except entropy. So all can be formulated in terms of the entropy. So I don't need any current, any axial current, only entropy. And this approach was formulated by Francesco and others. This is the answer for this approach. If we have here different result for the polarization, then it means that all is thermalized except for the spins. They are not thermalized. They are produced dynamically in this thermalized system. This concerns also the Valechka-like model. Also, the polarization in their model isn't thermalized. It is produced dynamically through spin-orbit interaction. So this is the difference.
Okay, so there is another question from Oleg, and then Shunwang.
Well, actually, I hesitated. I raised the hand to the, but then I thought it will be another discussion. But let me say a few words concerning this, for me, quite interesting point. And well, Francesco said that it's always thermodynamics, and in the case of what is called axial vortical effects, it was called in a different way, maybe first, but that it is also thermalization of Dirac field. Well, it's possible to say so, but also it's possible, I would say it rather in slightly different way, that this is effective theory, and thermalization includes only appearance of temperature and chemical potential. And there is also, this is of course terminology, there is also some practical differences. First, it's indeed the word chiral is a proper word. It's for massless quarks. And our first attempt just with Georgy Prokhorov, who is here, and Valentin Zakharov, was somehow to merge this effect by calculating the anomaly in thermodynamic way. Indeed, anomaly is there, an anomaly-induced current. But also, there is also some answer to Giorgio's question. The Gedanken experiment, I believe it is, and even maybe not only Gedanken experiment. The point is that in thermodynamic approach, in rigorous thermodynamic approach, if really all particles with spin are thermalized. For me, it's quite similar to thermalization in polarized targets, where it's magnetic field instead of vorticity, and here enters the magnetic field divided by temperature. So polarized target must be frozen target. And here, of course, in this way, all the polarizations have the same sign, and all the say force of spin 1/2 particles, and they differ only because of their mass. In the effective theory, which is formulated on the level of massless quarks, the sign of polarization is essentially dependent on the quark structure of hadrons. And here the conservation of axial charge plays more or less the role of quark-hadron duality. Maybe it can be considered analog of what is called 't Hooft consistency principle, that anomalies are the same on the level of fundamental particles and physical particles. There is not really the anomaly in the sense of non-conservation. There is only induced current, which is an essential feature of effective field theory anomalies. So just I would say again, there is definitely a thermalization. There is definitely a thermodynamics, but I would say that what again Francesco calls thermalization of field, this is better somehow to, I would instead, I wouldn't say better, but I would call it effective theory. Also, it's another maybe now disadvantage of this approach, because in rigorous thermodynamic approach, there is equation which immediately contains a particle momentum. So just it's possible to calculate polarization for particle with definite momentum. And calculating the current, the field and current, its dependence, there is no momentum. You need to integrate over momentum. It's dependent on x. And of course, we don't know what is x. And somehow calculating the axial charge is a sort of compromise. We integrate over x and get something average also over momentum. So this is for me somehow the different manifestations of thermodynamics in these two cases.
Okay, thank you. So Chun Wang, the next. Chun Wang.
Yes. I don't understand how do you calculate the extra charge for lambda and the lambda bar? Is it from the formula, the chiral-Voltke effect formula? So what's the difference between lambda bar in the extra charge?
Well, in fact, but if it is because this is a way we started to apply the statistics, maybe I can say, and Yuri make a comment. So just the point is that axial charge on the level of quarks and currents is just integral of zero of component. In order to identify axial charge with polarization, just it was done by analogy with ordinary charge. So we compare the matrix element of vector current, which is proportional to electric charge, and of axial current, which is proportional to polarization. Now, somehow by a sort, I would call it maybe consistency principle, if electric charge may be calculated by dividing total charge by number of particles. So also here polarization we get by dividing the axial charge by number of particles. And this explains the difference between lambda and lambda bar, because much less lambda bar are there.
Maybe a few other comments. So this is the density of the axial current.
Yes. Did you calculate the extra charge from this formula?
This is integration over x. This is integration over result surface, because in my case I did isochronous result in this calculation, precisely in this calculation. So d3x, this is integration of result surface. Integration of the density of this axial charge. So all this is all the charge of result surface, and then divided by number of particles which carry spin.
Okay.
produced by this axial current. So this is like that. So actually, this is a simple formula, and this is boost to the local rest frame of the matter, because the polarization is
Okay, we have, okay, guys.
defined in the
Okay,
local
thank
rest
you.
So we
frame.
have now
Yeah.
students' question. We have students. Rajiv Singh, please go.
Thank you for the talks, and I'm a PhD student, and I have just a very general question that
To
during
whom would you like to ask this question? To everyone or?
yeah, it's a general question to everyone.
Okay.
Yeah. Okay, so the question is that when you measure the spin polarization, then how do you subtract the lambda hyperons from the feed down effect? Means you only measure the polarization from the primary hyperons. So how do you subtract the secondary hyperons so that it does not affect the results of the primary polarization?
Sorry, subtract.
Yeah, so there's the question not for Yuri, actually.
No, that I would just want to
You want to answer this question?
No, I just subtract what from what I didn't quite catch.
Yeah, Francesco was doing, yeah, there were some people who doing some work on the influence of resonances and such things.
I think Takafumi can answer this question.
Okay, so please, Takafumi, could you please answer this question if you are still with us?
Yeah, sure. So for lambda polarization, so experimentally, we actually didn't subtract the feed down effect, but instead of that, there are several studies by using some model, how much the contribution of the feed down, then also considering the polarization transfer from the parent particle, can estimate the effect. And yeah, based on some model study, we know that the effect is roughly 15 to 20%. Is that the answer to your question?
So it's basically depending on particular models, that what will be the effects of the secondary polarization or hyperons.
Sorry, your voice was broken. Could you say again?
Yeah. I was saying that you said this is by particular model you found the magnitude of the secondary polarization of the lambda hyperons, which is around 15 to 20%.
Mm-hmm.
Okay, so it's basically on on particular models you find the different magnitude of the secondary polarization.
Yeah, it's model dependent.
Okay. Thank you.
Okay, Shu Guang wanted to ask something. Shu Guang, please. I see
yes,
your raised hand.
Okay,
Your hand
yes.
raised.
Can you hear me?
Yes.
Okay, so first I want to comment about the last question. From our calculation, indeed for lambda, there are about 10 to 15% of the spin polarization of lambda is from feed down. Although the number of all those lambda are about 70% are from feed down, but the feed down contribution to the polarization is not that significant, at least in our calculation. Then I want to ask two short questions still to Yuri. The first one is a technical question. How do you extract the temperature and the chemical potential from your calculation?
This is hydrodynamics, so then I have in my equation of state temperature and chemical potential and strange chemical potential, because here I need not simply chemical potential, but chemical potential strange and anti-strange quarks. Okay. So this is just all in my hands. So this is not kinetics.
Okay, so you simply I mean, you apply hydrodynamics to those low energy region.
Yes, I just continue my calculations from the RIC energy range to the low energy range. Actually, I can do it. Why not?
Okay, that's fine. Okay. Another short question is about the freeze-out condition. You said that you need the mechanical equilibrium to reach the freeze-out.
Okay, that freeze-out
mechanical equilibrium.
Yeah,
why is that?
I just analyzed the calculation that a little bit in another topic. I analyzed when this equilibrium is reached. Actually, I did my I proceed in simulations up to freeze out. About freeze out, technically, this is a little bit different from those I did in all my other calculations, like spectra, flow, elliptic flow, directed flow, because here it is a bit more difficult calculation. There, in all other places, I applied a differential freeze out, so which locally, when the energy density was reached, I stopped the hydrodynamical simulation. Here I did isochronous freeze out. So when average energy density in some central region reached my freeze out energy density, I stopped the calculation. So it is more rough, of course, but otherwise it is difficult to do it. So then I calculated all these quantities, chemical potential, temperature, and I have all in my hands.
Okay, thank
you. Cheminko, please.
Yeah, I have a questions. Maybe I should address to John Wang and also the talk about Yuri, because Yuri mentioned that some recent paper to be published in Physics letter B, which I just realized I never seen that paper, that by using corona model, that someone claimed they can explain the lambda bus polarization splitting, because most lambda produced at the corona, which gives smaller polarizations. And my question is the following: when Chung Wang's calculation using MPT, which is a dynamic model, so both corona core, they automatically include in the dynamic model. If I understand it correctly, he did not see any difference in lambda polarization. Am I right, Chung Wang?
Yes, I think so.
You mean this?
Yeah, I think that's a very schematic stretched model, because in John Wang used the MPT model, which is dynamic. Every particle participates dynamically, therefore automatically, corona core automatically included there. It's all there. And he did not see any difference in lambda polarization.
This is completely non-thermodynamical mechanism. That I agree. This is completely dynamical, no thermodynamics at all. Because they even in the core they calculate their polarization not according to thermodynamical assumption. This is just
how do they calculate the lambda polarization? They really calculate the n angle to n lambda k, then you calculate lambda polarization from that n-metric reaction.
They
must go using they use Glauber as the initial state to separate corona and the core. Pretty sure afterwards they must follow some kind of thermal hydrodynamic or transport approach. Otherwise, how do they calculate lambda polarizations? If they found first collisions, they all be completely washed out after the evolution of the system. I don't know. That's the first time I saw this paper. I don't know what's inside that paper.
No.
Have you read the paper?
I read it that not just from the very beginning to the very end, but I hope the most important places I read. So this is, to my mind, it's these are the most important assumptions, but there are other assumptions. For example, what is polarization in the core? In the core, they assume that at the moment of the production of the core, the polarization of lambda is 100%. The same for polarization of anti-lambda. Why?
That's acceptable. That's like in hydrodynamic approach, right? You assume in the hydro approach, everything's, there are cores, right?
But 100%, 100%.
Yeah, so it's, you know.
So why don't ask me why, and they don't ask, they don't answer also why. After that, this polarization of lambdas and anti-lambdas just relax with some relaxation time. This relaxation time is a fit parameter. This is why here time is labeled.
So, I see. I got you. All right.
So this, if the time from the production of this core is 1.5 Fermi, then we have this strong polarization. If more than this low polarization. So I have many questions.
Okay.
That even maybe even more questions than answers.
All right. Thank you.
Yeah, that's okay.
Shuguang, would you like to ask still some question?
Oh, yes, I want to ask a question for the first two talks.
Oh, very good, yeah.
I noticed in the first two talks, both Takafumi and Xiaoliang showed the experiment the data for the rho 00 of phi. However, they used two different figures. In Takafumi's slide, he showed that the rho 00 of phi, I mean the centrality in Takafumi's slides is opposite to that in Xiaoliang's slide. Is that true?
Yes.
So I want to check with the experimentalist, or is a typo? What is why is that?
So the picture I used is taken from Quark Matter 2018, and I think Takafumi's picture is from Quark Matter 2019. So there is a difference. So I also want to know which one is correct.
Yeah, at least for Alice, I took the figure from the paper published, and for Rick, indeed I took it from the Matter 2019. The data point itself should be same. It's preliminary.
But the label for N part and the centrality are reversed in reversed order.
Okay, guys, I think we are slowly coming to the end. I guess I see Francesco's hand. So maybe combine some physics comment together with organization. Kind of comment.
I want to ask you some question for the second talk.
Yes, so please go ahead, and then we, I think, close the session.
Yeah, the question is so to Shia, right? The question is in slide number 17. He wrote that Fx, Fy are larger than Fz for the say dependence of the polarization as a function of the azimuthal angle.
Yes.
So Can you show that slide so that maybe that people can follow?
Okay.
Yeah.
Yeah, this one.
This one, yes, sure.
Yes.
So you said, well, no, but not maybe I was wrong. But at some point maybe it's not. This is not the slide I meant. But you wrote at some point that fx and fy are larger than fz. Ah, yes, in the sorry, yes, in this plot, right? But so this I could not get, because so maybe I'm missing something in the definitions. The amplitude of the polarization, say, along the various direction in our calculations, that with URI, for instance, we always saw in hydrodynamic simulations that fx and fy are smaller than fz at large energy. Sorry, yeah, are smaller than fz at large energies.
Okay. Maybe because you are calculating the second order harmonic in transverse polarization, and here fx and y we are talking about is the first order harmonic.
Ah, okay, I see.
And that is odd function of rapidity. So
right.
If you do not,
okay, yes. I get it. Yes, because you have sine and cosine and not sine 2. Okay, yes. It's clear. Yes.
Oh well, Francesco. So we are coming to the end, I guess, with time.